All right, we have arrived. We have arrived at our first major theorem. And this is a theorem that you've used already in the class a little bit. This is the theorem that says that if a set has n elements, then it has 2 to the n subsets. So if a set has 3 elements, then it has 2 to the third, or 8 subsets. And here we will see why. And we will see why using this ingenious representation of the subsets as binary numbers. All right, now looking at this, I realized that that my proof here doesn't actually cover one special case, and that is the case that n equals 0. So let's deal with that. Okay, so if the set A has 0 elements, then that means that A is the empty set. And the empty set has just one subset, itself. The empty set is a subset of itself. Right, remember this is true because we proved that the empty set is a subset of all sets, and we also proved that every set is a subset of itself. So in the empty set case, they both say the same thing. So that's one subset. So if a set has 0 elements, then it has 2 to the 0, which equals 1 subset. Okay, so I've proved it now for the special case that n is 0, and now we'll prove it for when n is greater than or equal to 1. All right, so we start by stating the assumptions. We assume that A is a set with n elements. And now I'm going to write the set A like this. Now, how do I know I can write it like this? Right? Am I being general enough? I am being general enough. Because, see, I'm not saying what the elements are. I'm just saying that whatever they are, I'll call one of them A1, and I'll call another one of them A2, I'll call another one of them A3, and so I'm just giving names to them. I'm not saying what they are. So yes, I can do this and still be general. Okay, so now let's look at our table. We've seen this table a couple times in previous videos. Now over here, we're going to assume that I have all subsets of the set A. Now, why can I assume this? Well, let's see. We know that A has subsets, right? We know that it has subsets. So let's just say we've listed all of them here. What's important is what we do with all of these subsets. Okay, so we know that there are subsets of a set. So I'm just going to I'm going to theoretically list all of them here over to the left, over here on this left-hand side. So this is all subsets. All right, now each of these subsets has a binary representation. We've already seen how to do this. But let me, to jog your memory, just do it again. Let's see, we have A1, A2, A3, AN minus 1, and AN. And where that 1 is in, 1 stands for is in, and 0 stands for is not in the set. All right, and starting with this one, right, we see that A1 is in the set containing A1, and none of these other elements are in there, right? So that's how we get that code. Similarly with A2, the set containing A2, A1's not in there, A2 is, and nothing else is. That's how we get that code. AN, the set containing AN. Well, let's see. AN is in there, and nothing else is. That's how we get that code. All right. A1, A2. A1's in there, A2 is in there, and nothing else. That's how we get that code. Let's see. How about this one? Let's see. A1 is in there, A2 is in there, and AN is in there, but nothing else. That's how we get that code. All right, and then lastly, looking at this one, this is the set A itself. Everything's in there. That's why we have 1, 1, all the way across. That's how we get that code. All right, now I think you can see by the way that we make these codes that since all of these are different, if we write out all the different subsets of the set A, that by the way that we make the codes, all of these are different. All right, all of those are different. And now we could make this extra column here like we did in the other examples and like you did in the homework, or you're going to do. And let's see. So now because all of these are different, all of these have to be different as well. Now you might say, why do they all have to be different? Well, it goes back to that idea that I talked about where these are the binary representation and the base 10 representation. Those are just ways of representing a number. They're not the actual number. Right, so the number, so if all of these are different, then whatever number they represent is going to be the same number that is represented over here by its base 10 representation. So if each of these are different, each of these over here has to be different as well, because they're just different ways of saying the same thing. All right. And so this first one would be 0, the number 0 in base 10. These are all different. You got a bunch of different numbers along here. And then we get to this last one. And the question is, what is this one? What is that number? And now we'll figure that out. All right, so we have its binary representation. 1, 1, 1, 1, 1, 1, 1, 1, 1, n ones. So there's n ones there. So what number is that? Okay, now remember that 1 plus x squared plus x cubed plus x to the n minus 1 is equal to x to the n minus 1 over x minus 1. All right, I'm definitely going to need more room here, but that's okay. All we really need is this last little bit. Okay, we could think of this one here as x to the 0, right, because x to the 0 is 1. All right, so we proved this I proved this in just a little bit ago. All right, another way to write this, now because you can write addition in any order, I could write it like this, right? I could write it as x to the n minus 1 plus x to the n minus 2 plus let's say x squared plus x to the 0 equals x to the n minus 1 over x minus 1. Okay, so I'm going to write it like that. All right, so now binary. So the binary, so what does this number represent here, right? What does this number represent in base 10? All right, so this is 1, 1, 1, 1, 1, yeah, so 1, 1 or something, I don't know, 1, 1, 1. Okay. Now remember how we would figure this out, right? We would start at, we'd have 2 to the 0. So this would be 1 times 2 to the 0. Plus 1 times 2 to the 1 plus 1 times 2 squared. Okay, I'm running out of room here, but I'll make it work. Okay. Oh. Okay, right, remember when we did, so just to jog your memory, remember when we did something like this? 1, 1, 1, what number is that? Right, let's see, actually we did this with 4, right? We did this with 4 in the previous example, 1, 1, 1, 1. This is 1 times 2 to the 3rd, so you always go 1 down, right? Plus 1 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0. Right, that was that number there. And that came out to 15. This was 8, 9, 10, 11, 12, 13, 14, 15. That came out to 15. All right. So same idea here, right? That's why we go, that's why there's n here. That's why we go to n minus 1 there. Okay, so now let's think, okay, what is this number, right? What is this number? This is In binary, we read it like this, right, with n of these here, and there. That's how we would represent it in binary. Well, that's just 1 times 2 to the n minus 1. Right? Okay, and so now we can use this formula to figure out what this number is. Right, so we're putting a 2 in here. A 2 there. 1 times that, that's exactly that, right? 1 times a 2 there. 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 So this is equal to 2 to the n minus 1 over 2 minus 1. 2 minus 1 is 1, so that's just 2 to the n. Oops. And the exponent minus 1. And so now we figured out that this is 2 to the n minus 1 right there. Okay, so using that formula, we found that that was 2 to the n minus 1 right there. Written in base 10. And so how many subsets are there? And so now how many subsets are there, right? So remember, this is a one-to-one correspondence between, or a bijection from all of the subsets to all of the base 10 numbers, between 0, all the base 10 integers between 0 and 2 to the n minus 1. So let's see, there's how many numbers are there here? Right, there's 2 to the n minus 1 numbers from 1 to 2 to the n minus 1. And so how many subsets are there? So then the number of subsets is 2 to the n minus 1 plus 1, or 2 to the n. And that's it.